Hello everyone, this is Dr. Lennon, and today we're going to talk about using integrals to calculate volumes of some objects. We're going to look at the disk method and also the washer method, which basically works when you take some fairly typical formulas, but then you consider rotating them about maybe the x or the y axis. So, obviously the idea is to create, let's say, three-dimensional figures by rotating graphs of two-dimensional objects. Right, you could look even, so for example, maybe you have something simple like, just we're looking at y equals x, and we're just looking at a particular subsegment of that. Maybe we want to rotate that about the x-axis, and then all of a sudden, what happens is you have some three-dimensional figure that is in fact just a perfect cone. So my picture is not the best. Let me try again. Problem with this tablet I have to draw on. Erasing is kind of, you have to erase almost everything. But I think you get the gist. You have something here and here. And again, we're just revolving this. And we get this three-dimensional object. So we can find volumes of those three-dimensional objects because as we're rotating, we're actually just we're getting kind of circles that are ever expanding until we get to the end of the interval that we're concerned with. So essentially this is kind of like integrating combined with the formula for the area of a circle, pi r squared. So and we can change things around for the y-axis like we saw when we were integrating regions between curves, but we'll just write this here for the x-axis. But you can appropriately switch around the variables and do this rotating around the y-axis as well, and we'll look at some examples there. But let's let x be, or let's say f be continuous. And for this theorem, we'll just say that f of x is greater than or equal to 0 on this specific region that we're trying to perform this revolution AB. So if the region R, capital R, bounded by the graph of F, the x-axis and the two vertical lines x equals a and x equals b revolved about the x-axis to give us that three-dimensional figure. The volume of the resulting object is given by, the volume is just the integral from a to b, and normally it would be pi r squared, but the radius is changing. It's just the distance of the y value of your function to the x-axis. So we can really just replace the radius in the area formula by f of x. So it's just pi times f of x squared dx. So this thing is acting like the radius. So we would say this is the disk radius. Okay, so let's look at some examples of how to use this, and then the washer method is really just the disk method, but you're kind of subtracting some inner tube. So really you've just got the difference of two functions. So we'll do a few of these examples, then we'll talk about the washer method, which is really just kind of applying the disk method to when you're subtracting two functions. You have an outer radius and an inner radius. But let's look at this first example. So let's consider f of x equals the quantity x plus 1 squared. Find the volume on 0, 2 by revolving f of x about the x-axis. So if you think about this, this is really just the typical parabola x squared translated to the left one unit, right? We're applying x plus 1, that change of variables inside the parentheses, so that would just rotate the typical parabola to the left one. So essentially, if you want to think about the picture here, the picture is just, we have some parabola. We've rotated the left one, so it's kind of, bottoming out here now and coming up here. We only care about, it would actually, in fact, go up over here. But we're just looking at the specific region between 0 and 2, let's say, and then kind of what happens is we get the mirror image, and we're just rotating, and this is our final one right here. So we've got that kind of like rotated section that we're trying to find the volume of between here and here, right? Not the best picture in the world, apologies for that. But what do? We just set it up according to exactly how the disk method told us to operate. We just integrate from 0 to 2 of pi times the f of x, which is acting as the radius, squared. So what do? The easiest way to integrate this is, we forgot to square. So the function is already squared, and then we need to square that result. So our volume that we're trying to figure out is 0 to 2. We can pull the pi out front if we want, and then what we really have is x plus 1 to the 4th. Right, and then that's a pretty easy U-substitution because the derivative of the inside is just 1. So we don't really have to worry too much. We can just kind of add 1 to the exponent 4 and then divide by that. So really we're getting pi over 5 of this function, x plus 1 to the 5th power from 0 to 2. And we're plugging those in and subtracting, right? So we get pi over 5 times, that's going to be 2 plus 1 to the 5th power minus pi over 5 times 0 plus 1 to the 5th power. And that comes out to, in the U substitution, I did make one small mistake there. When we substitute U is equal to x plus 1, so we are going to have to change our limits. So that's going to go from 1 to 3, not from 0 to 2 anymore, right? Because the U substitution for this part, when you're integrating, right? So essentially the U sub is U equals x plus 1, and then du is equal to dx. So from the U substitution, the limits 2 becomes 3, and 0 becomes 1. So this is the U substitution that you would have to perform to find that antiderivative. Anyhow, you can plug this in, you can just do the arithmetic, and you end up with 242 pi over 5. And that's it. So yeah, sorry about that little mistake there. But let's go ahead and look at some other examples with the disk method and see if you can catch on. Okay, let's look at some other examples from the book. So this next one is like the one I drew for the original idea. We're just going to graph the line and then rotate it, so we'll end up getting a cone. And then that way we can check it with the formula from geometry to make sure we actually do get the same thing. So this example, I'm just going to copy and paste in from the book. I'll probably do that so the pictures look a little bit better, so things are more clear. It's always drawing pictures by hand can be a bit of a challenge. So 1 second, I'll paste that in, then we'll get to it. Alright, so this is the example we're looking at. Again, pretty straightforward, but when we rotate, we should just be getting a cone. So the volume here, again, we're just going to take pi, and we're integrating the x values from 0 to 1, and then our function that's giving the radius is 2 minus 2x, and we want to square that because it's acting like the radius. So I'll actually do the U-substitution this time to make sure I don't make any more mistakes. So we'll write down all the steps. So let's let u equal, you could actually multiply it out too, and just go term by term, but substitution tends to be a bit easier. So du is going to be minus 2 dx. Again, the limits here, what's going to happen? Well, when x is 0, so when x is 0, 0 becomes 2 minus 0, which is 2. And when you have 1, we get 2 minus 2, which is 0. So the limits kind of flip there. So anyhow, this becomes pi times the integral from 2 to 0 of, so we're going to be dividing by -2, in fact, from the -2 that we divide by, and then we get u squared du. Okay, so let's continue up here. We end up with negative pi over 2 times u cubed over 3 from 2 to 0. So the 0 actually, the 0 term goes away, then we're going to be subtracting the 2 term. So in fact we get negative pi over 2 times 2 to the 3rd power over 3. So one of the powers of 2 will cancel with the 2 in the denominator, so we should just get 4 pi over 3. And that should be the volume. So let's think about the cone that we have here. The typical formula for the cone is it's 1/3 times 1/3 times pi r squared times height. So if we thought about this cone, what would the height be? Well, the height would be 2, the radius would be 1, so you would get exactly 4 pi over 3. So this agrees exactly with the formula for the volume of the cone, right, that we learned from geometry. So that's it for this example. So let's go ahead and do one where maybe we want to rotate around the y-axis instead of the x-axis, and we'll see how we have to change the behavior of the variables. So in this example, we're finding the solid of revolution formed by rotating around the y-axis. So again, this thing is going to kind of look like a bowl almost that has kind of like a square bottom, right? You can imagine, right, you've got this shape, and then you would extend it over here, and then you would rotate, so we'd get this squared off bottom kind of right here. And this whole thing would be being rotated. So you're kind of getting like a bowl thing with like this square bottom. Anyway, so that's the solid of revolution that we're forming here. This thing. So what we have to do here is actually solve for both of these in terms of x, right? So we have y equals x cubed. So we want to raise both sides to the 1/3 power, take the cube root. So really y to the 1/3 power is equal to x. And then technically this is a washer method because we have two curves, right? The length between those two curves, x equals 1 and y equals x cubed, is changing. So, I mean, it's really not so similar, or it's not so different. But the washer method from the disk method is basically just saying what you do is to find the volume of this region. What we do is we have the integral, so we have pi times the integral, from a to b of, say, f of x minus g of x quantity squared. So we have a difference in radiuses because those are changing. They're not constant radiuses. So we have our two functions here, x equals 1 and x equals y to the 1/3. So that's what we're going to use here to get the volume. So our volume is pi times the integral from 0 to 1. Remember, we're integrating from the bottom to the top, and then we need to use 1, the outer radius, minus the inner radius of the bowl, which is given by that y to the 1/3 dy. So integrating that, we should get pi times y minus, so we're going to have to add, I forgot to square this whole thing. Oh, sorry about that. I keep forgetting to square everything. I wrote it down when I wrote the formula, but then I didn't apply it there. So anyway, let's go ahead and raise this to the second power and do it properly. So usually with these, you're often going to get a chain rule unless you actually just want to go term by term. But let's go ahead and use the chain rule here. So what are we going to do? We're going to let u equal 1 minus y to the 1/3. So du will be minus 1/3. Sorry, I was doing the derivative for some reason. So we add 1 to the power, and then we multiply by the reciprocal. So the new power is going to be 4/3, so we're going to get 3/4 times y to the 4/3. And then we're going to, I just realized I've messed up. In fact, the washer method, you're subtracting two separate areas, right? So we would actually just square each function separately. So that's another small one. So the washer method should be f of x squared minus g of x squared. So in effect, we're going to be squaring each formula here. So it would be 1 squared minus y to the 1/3 squared. So we're actually, in fact, not going to require the substitution at all. It's just going to be a straightforward integration. So this is going to be pi times the integral from 0 to 1 of 1 minus y to the 2/3 dy. And now we can integrate. So we get the pi, and then we're going to have y minus, so if you add 1 to that power, you're going to get 5/3. So you're going to get 3/5 times y to the 5/3 from 0 to 1. So if you plug in those numbers, zeros, everything's going to go away. When you plug in 1, you're going to get 1 minus 3/5. So we just end up with 2/5 times pi. So in this example, we've both introduced the washer method and also integrated with respect to y, so nothing too difficult there. So let's move on and do a couple other ones with the washer method. As I've said, we're just subtracting the two functions and squaring each one of them separately. So it's almost like you're doing two disk methods and subtracting them. So nothing too complicated about that. Okay, so here we have another washer method, and we're just rotating about the x-axis. So the volume we can set up pretty straightforward. The volume here is just we're integrating starting at pi over 6 and going to 5 pi over 6. And the top curve is 1 minus sine of x, so we're doing 1 minus the, is that the bottom curve? Yeah, so sine of x would go through 0. So in fact, the top curve looks to be sine of x, and the bottom curve looks to be 1 minus sine of x. So let's go ahead and do that. You got to think about the sine curve. So we have sine squared of x minus 1 minus the sine of x, quantity squared. And don't forget to multiply by that pi in front of our integral. So that's, again, just from the washer method. So what are we getting here? We're getting pi times the integral from pi over 6 to 5 pi over 6. And we have sine squared x minus 1 minus 2 sine of x plus sine squared of x. So simplifying, the sine squareds of x are going to cancel when you distribute that negative, so we're really going to get pi times the integral of pi over 6 to 5 pi over 6 of 2 sine of x minus 1 dx. So that is not such a difficult integral. The antiderivative of sine of x is going to be minus cosine of x. So we have pi times minus 2 cosine of x minus x, and we're going from pi over 6 to 5 pi over 6. Okay, so let's do the arithmetic. We're going to get pi times negative 2 cosine 5 pi over 6 minus 5 pi over 6. Okay, then when you subtract, plugging in the pi over 6 is distributing the negative is going to just make them both pluses. So we're going to get plus 2 cosine pi over 6 plus pi over 6. And let's see what this all comes out to. Whoops. Can I do that last one? Yeah, okay. Good, so let's see. Cosine of 5 pi over 6. What is that going to be? That's going to be in quadrant 2. It's going to be negative radical 3 over 2. So we're going to get pi times, so negative radical 3 over 2 times the negative 2 is going to make this positive radical 3. Minus 5 pi over 6 plus pi over 6 is going to be minus 4 pi over 6 or minus 2 pi over 3. And then plus 2 cosine pi over 6. Cosine pi over 6 is going to be, so that's also going to be radical 3 over 2 times the 2 is just going to give us a plus a radical 3. So I don't know exactly how they want us to write this, but basically I'm getting pi times 2 square root 3 minus 2 pi over 3. I don't know, probably maybe they would get a common denominator. If you would get a common denominator, you just put everything over 3 and distribute the pi. So I looked up how the solution was written. What they did was they pulled out 2/3 rather than getting a common denominator. It doesn't really matter. This would be fine. But if you pull out 2/3, you're taking out a 2, and then you would have to take out a 1/3 from the first term. So you would end up with square root of 3 over 3 minus just pi. Oh, I forgot the pi in front. So 2/3 pi should be in front. Let me fix that. Or 2 pi over 3. We could just put it on top of the numerator there. Anyhow, that is it for this example. So let's go ahead and do one more, and that will handle it for disk method and washer method. So for our last example, we have another solid of revolution, but this time what's actually going on is we have a solid of revolution that is not either the x-axis or the y-axis. We have something that's parallel to the x-axis. We're rotating about the line y equals 1. Now there's a few ways to handle this. You could actually just kind of translate the y equals 1 axis so that it's down exactly on the x-axis, and then maybe you would flip things around and alter your formulas that way. But what we're really concerned about, probably the easier way to do it, is thinking about the picture. That's all we really care about, is what does this radius look like in general, a general form of the radius. And it's just going to be this 1, this height, minus the formula for the value down here, which is just the 1 minus the square root of x. So that's essentially our radius, and that's what we're going to want to integrate in the washer method formula. So the volume here should just be the pi times the integral of this 1 minus the square root of x squared dx, and we are going from x values 0 to 1. So that's exactly what we have here. We have the 1 on top, the y equals 1, minus the formula for y on the bottom, 1 minus the square root of x. So this actually just will simplify to pi times the integral from 0 to 1. When you distribute, you get 1 minus 1, so those cancel, and then plus square root of x. So we've really just got the square root of x quantity squared dx, which is just pi times the integral from 0 to 1 of x dx, which is the simplest of integrals to compute, right? We just have pi times the integral of x squared over 2 from 0 to 1, and so our answer here is just pi over 2. So again, we see that we can in fact rotate or revolve about other lines rather than the x-axis and the y-axis. We just have to think about the radius that's changing and what that formula looks like. So that's it for volume by slicing. We'll go ahead and look at the shell method next, which is a much more general method. Sometimes it's harder to visualize, but when you know how to set it up, it works kind of every time, and it's another technique to help us find volumes of these three-dimensional objects using integrals. So this is Dr. Lennon signing off.